the chalklands of the Berkshire Downs. Far from the towns and busy roads is an unmarked gate, and through the gate, beyond the steel door, lies a concrete vault. Here on the 20th of June 1978, seismic instruments responded to a distant earthquake. Some minutes later, about 600 kilometres north in Eskdalemuir, the same event was recorded. And at different times, in different places, seismic stations all over the world recorded the telltale traces from the same event. We'll find out where that earthquake happened later in the programme, but first, what is an earthquake? This limestone quarry in the Pennines is peaceful enough now, but it can easily be turned into a site for demonstrating some fundamentals about earthquakes. That they involve rapid movements of parts of the crust with the release of large amounts of different kinds of energy. Well, that's certainly an example of rapid earth movements, in this case caused by the helping hand of some TNT. But we've only shifted about 10,000 cubic meters of rock, whereas in large earthquakes, millions of cubic kilometers are moved, and all at once. For example, in the Alaskan event of March 1964, some 200,000 square kilometers, an area the size of Scotland, was moved instantaneously to a depth of 30 kilometers, and by as much as 7 meters in places. Nature makes our efforts look feeble. This block is about 5 cubic meters, and it takes most of the power of this machine to shift it slowly. The friction of the block with the ground generates heat and sound, and the same is true when blocks of the Earth's crust move against each other. As you know, the Earth's outer skin, or lithosphere, is constantly moving, and the results of these movements are often recorded in the rocks. These sandstones and shales in Devon were eased into this contorted pattern some 200 million years ago, accommodating a considerable shortening of the crust. To fold like this, the rocks must have responded plastically to natural forces. But in other cases, the rocks may not yield in this way, but break by brittle fracture and develop shears. In this case, compressional movements have caused a reverse fault, and the result is a small shortening of the crust. Natural extensional forces also occur and may result in normal faults. These two types show clearly the direction of relative vertical movements of the crust. Of course, most faults have a horizontal component of movement too. Other fault planes are vertical and are not always easy to identify in the field. But there is at least one large vertical fault in the quarry. This scar up the hillside gives us no clue as to the direction of movement across it, but it can be traced away from the quarry across Derbyshire. Any of the faults just shown could have caused major earthquakes if they had moved violently. So the concentration of faults in Derbyshire tells us that there must have been sizable earthquakes right here millions of years ago. Britain is riddled with faults, ranging from the small fractures in the quarry to the large-scale fault displacements further north. Their present displacements of tens of kilometers result from many jolting movements, but even these were small. Over in California, the whole Pacific plate today is slipping slowly past America in a series of jolts. The junction occurs along the San Andreas Fault, which, as you know, is a highly active seismic area. This activity has been studied in great detail, and it's probably the area where earthquakes are best understood. After the famous 1906 San Francisco earthquake, a seismologist called Reed, who worked along the San Andreas Fault zone, put forward a theory to explain how earthquakes occur. He noticed many examples of the offsetting of roads, fences, tree lines, etc. near to the fault due to sideways creep, structures like pipes and railways crossing the fault became buckled. All this movement occurred without noticeable earth tremors, and only when abrupt movements occurred were shocks felt. Reid had the idea that vast amounts of energy are built up as the opposing blocks of land deform due to shearing stresses, until eventually the frictional forces locking the fault are overcome and the blocks jolt into their new positions. This releases the strain energy stored in the deformed blocks, which are now displaced, but once again undeformed. This elastic rebound releases all the stored energy, which travels outwards in the form of seismic waves, signalling an earthquake. But what effect does the release of such energy have on structures in its path?
Well, I didn't touch it, but these rocks here were quite capable of transmitting the energy of my hammer blows into the ground so that the hut eventually fell down. But notice that I had to reduce the distance of my hammer blows from the hut in order to effect its complete destruction. And the same's true in real earthquakes. We have to go to further and further distances from the source or focus to see decreasing intensity of destructive effects. Now, we can't simulate natural earthquake movements in this quarry, but what we can do is to set off a series of explosions, and although our simulated seismic events will be relatively small, we can observe their destructive effects at close hand. Observations of the effects of earthquakes on everyday objects allow us to estimate the intensity of the event. Now, let's go and observe the effects of some similar explosions on some objects inside this shed. We have some objects in here that should be a bit more sensitive to the effects of ground motion. Okay, nothing very spectacular there, but it's details of the effects of motions like the mug swinging on the rack up there that Macaulay used to set up a 12-point intensity scale which describes the destructive effects of earthquakes. And mug swinging around would be number 2 on his scale, second lowest. But although the mugs on the rack started swinging, the things on the table weren't affected at all by that explosion. So let's try a slightly more powerful one. Good, well, things are hotting up a bit in here, and that was about Macaulay 4. But you should remember there are another 8 points to go up that scale. So, let's just try increasing the size of our explosion by a factor of 10. Well, a real earthquake wouldn't have looked quite like the effects of that explosion, but the damage you see is equivalent to about 0.7 on Macaulay's intensity scale. So the difference between the mugs rattling that we saw earlier and this kind of damage is 3 points on the Macaulay scale. And to achieve that, we put in 10 times as much energy into the ground. Now, of course, we could increase the energy by another 10 times and go up 3 more points on the Macaulay scale. And that would be 6 points for a 100 times increase in energy. But the kind of effects that you've been seeing, the mugs rattling and the damage that's been done to this hut, is obviously important for people who live in active seismic areas. But more important still, it's important to see how far away you are from the earthquake. And so before the last explosion, I set up some of these seismic intensity detectors so that we could examine the effects of the earthquake, or the explosion rather, at different distances from its source. At 30 meters, the energy from the blast transmitted through the ground was sufficient to knock over the cup. But at 60 meters, the cup was merely shaken and some of the tea was spilt. Whilst at 90 meters, no effects are recorded. So distance from an event has a very marked effect on intensity. That's very fortunate, for if earthquake energy was not dissipated in its travel through the Earth, then no man-made features would exist today. As effects decrease away from the source, it's possible to correlate the effects and produce an intensity map. Imagine that the whole quarry floor had been covered with teacups or mugs. Then it would have been possible to map the edge of an area where all the mugs fell down with a line, and another line for the edge of the area in which tea was spilt. These lines of equal intensity of effect, or isoseismals, can be used in a real event to locate the centre of the event, or epicenter. This method, however, has many drawbacks because it relies on observations of past events and interviews with survivors who are often shocked in the true sense of the word. What we actually need is a more precise physical measurement that we can make of earthquakes. And if we measure the ground acceleration that's produced during an earthquake by the energy that's transmitted through from it, then obviously we've got a much more physically precise quantity. Seismometers are designed to measure just those accelerations, seismometers like the ones you saw earlier in this program in the vault. But even such instruments have not always been quite so sophisticated.
They certainly haven't. This is the model of the first instrument ever built to detect earthquakes. It was made in China in the 2nd century by the philosopher Cheng Hung, and although it's really simple, it's reasonably sensitive. So how does it work? Any seismic wave will cause this pendulum to swing, which knocks a ball out from the mouth of this dragon into the ever-ready frog beneath. The device also tells us the direction of the waves because of the way the pendulum is connected to these rods. When a seismic wave moves the pendulum, the direction is recorded by a particular dragon, or if a wave comes from other directions. Well, seismometers have progressed since Cheng Heng's day, and since the 1960s, instruments such as these have been used to detect and locate earthquakes. Even though we've removed the case, it's still not as pretty as Cheng Heng's, but it's a lot more sensitive. Inside is a heavy mass mounted on springs. This instrument is designed to detect vertical waves, so the mass can move up and down. At the seismometer station, the body of the instrument is fixed firmly to the ground, and when a seismic wave passes, the body moves with the ground, but the heavy mass stays where it is because of its inertia. So how is the movement recorded? There's a coil in the centre of this mass. You can't see it, but when there's relative movement between the body and the mass, which is magnetic, an electric current is produced, which we can show you here. It's recording background noise in the studio all the time, so let's give it a shock or two. And an earthquake wave causes a similar vibration, which can be recorded either on magnetic tape or on paper. This seismic trace was recorded at S237, the station we mentioned earlier, which is one of the worldwide network of seismic stations. Records like this are used to find where an earthquake occurred, the epicenter, and how big it was, its magnitude. And I'm going to use this record to show you how it's done. First, we'll look at how far away the earthquake was. Here's the P wave arrival, and here's the S wave arrival, and these time marks are 1 minute apart. The travel time of seismic waves from the earthquake to the seismometer depends on the distance of the earthquake, and seismologists have been able to determine the average travel time of P and S for an earthquake at any distance. But here we don't know the travel time of these waves, and we don't know the exact time the earthquake occurred. But there is a time we can measure from the record, and that's the time between the P and the S arrivals, which on this record is about 4 minutes. This difference is due to the lower velocity of shear waves in the Earth compared with compressional waves. We can measure this accurately and use this time difference, the S minus P time, to find the distance of the earthquake from standard tables. In this case, the earthquake is 2,500 kilometers away. But we don't know in what direction. To find the epicenter, we have to use records from at least 2 other stations. These other 2 records are from seismic stations in New Delhi in India and College in Alaska. These are the P and S wave arrivals for New Delhi, and the S minus P time is 7 minutes and 2 seconds, so we can find the distance of the earthquake from New Delhi. It's 5,280 kilometers. We can do the same thing for College, which gives us 8,250 kilometers. Now we have the distances from 3 stations to the earthquake. It's possible to find the epicenter using a globe. Starting here in Scotland at Eskdalemuir, we know that the earthquake occurred 2,500 kilometers away, and the distance from here to here on the scale of the globe is 2,500 kilometers. So the epicenter must lie on this circle. Our record from New Delhi, which is here, showed the earthquake was 5,280 kilometers away. So if I draw another circle, it crosses the Eskdalemuir circle here and here, giving 2 possible epicentral locations. To decide which of these 2, we need information from the 3rd station, which is College over the other side of the world. And the epicenter will be where these 3 circles meet, here in Greece. And this is how the world learns about it. This may seem a rather rough way of locating an earthquake, but before the development of computers, this was how it was done. These records are also used to find the depth of the earthquake. If we look again at the Eskdalemuir record, this is the P wave arrival, and here is a later arrival. The waves from the earthquake travel not only directly to the station, but also to the Earth's surface and reflected there. This wave is called little pp, and it arrives after the P wave as it's travelled further. The time difference between the arrival of these 2 waves is a measure of the extra distance travelled by the little pp wave, from which the depth of the earthquake can be calculated. For this earthquake, this time difference means that it was 70 kilometres below the Earth's surface. These records can also be used to calculate the magnitude of the energy released and not just the damage caused, like the intensity scale. We get this from a combination of the amplitude of the waves, like this, and the distance of the earthquake, which we've just found. The seismometer is calibrated so that the amplitude is related directly to the ground motion, which in turn depends on the energy released in the earthquake. As with intensity, there's an accepted scale of magnitude, the logarithmic Richter scale. The largest earthquake yet recorded measured 8.7 on the Richter scale, which is some 1,000 times greater than this earthquake, which had a magnitude of 5.1, but that's more than enough to cause considerable destruction. We can use these records to find one other thing. The P wave on the Eskdalemuir record has a first motion that is initially downwards, and this indicates an initial stretching. It's called a dilatation. College is the same as Eskdalemuir, but New Delhi has a first motion that is upwards, so this is a compression. Now, why in some cases is the first motion of the P waves compressional and some dilatational? That depends on the orientation of the fault plane and the direction of movement along it. As most earthquake-forming faults can't be detected at surface, this type of instrumental data is the only way of finding this information. This is called a fault plane solution, and you'll find more details in Block 2. The disadvantage of using the world network of seismographs to find the location of magnitude of earthquakes is that it can't be done quickly, that it takes a few months for seismograms from remote stations to be collected. This time delay in accurate location was a particular nuisance when the seismographic network was used to detect nuclear explosions, and most work of this kind is done using arrays of seismometers. One such array is at Eskdalemuir. It consists of 2 lines of vertical component seismometers, like the one we showed you in the vault. The seismometers are about 2 kilometers apart. All these seismometers record on magnetic tape. If, for example, an earthquake occurs to the northeast of S237, the seismic waves will reach the seismometers nearest the northeast first. So the difference in arrival times can be used to give the direction of the earthquake. The distance of the earthquake is found from the speed the wave crosses the array. A wave from a nearby earthquake reaches the array travelling almost horizontally and crosses it slowly. A wave from a distant earthquake comes from a more vertical direction and crosses the array much faster. So the speed of the wave across the array gives the distance of the earthquake. And with a large computer, this can be calculated almost instantaneously. In fact, the S237 array is programmed to search continuously through all directions for earthquakes or explosions. Arrays such as S237 represent the finest of modern seismometers, but they're unlikely ever to record an event like this. Here's the timescale. This is 10 minutes. The ground shaking at this seismic station is continuing for over an hour, very different from the 3 records we've just seen, which shook a seismometer for about 20 minutes. And this record comes from a rather unusual seismometer station. Part of the Apollo research program was to study seismic events on the Moon. The lengthy reverberations found in lunar events may result from ringing in a strongly welded crustal layer thought to occur right round the Moon. This layer resulted from the many meteor impacts that characterize the cratered surface we see from Earth. By placing a number of seismic stations on the Moon, it was possible to record interior activity, and so moonquakes were discovered. The remarkable thing about these moonquakes is that they occur far deeper than most earthquakes on Earth, around 600 kilometers. At that depth, there's a boundary between the lithosphere and a partially melted zone called the lunar asthenosphere, thought to be at the center of the Moon. So on the Moon, seismicity is providing the key to uncovering the structure of the Moon, just as on Earth.